So in this lecture, we're going to look at our first reaction of carbonyls, and this is going to be a nucleophilic addition of carbonyls, where that nucleophile is a hydride. So hydride addition to carbonyls. Now, nobody calls this hydride addition of to carbonyls. This is the reduction of carbonyls. Because if you recall, reduction can be defined as the addition of an electrophile, removal of oxygen, or an addition of hydrogen. And so that's what we're doing here. So we're reducing carbonyls, and this is similar to the carbonyl reduction lab. So as you're, if you're thinking about the other things happening in the course, the carbonyl reduction lab has to do with this reaction. So again, this is a nucleophilic addition reaction to a carbonyl. Don't know if you can hear that. There's a baby crying in the background. Sorry about that. So nucleophilic addition to carbonyls, where the nucleophile here equals an H minus. So what we want to do when we look at this reaction is consider, first of all, a general mechanism. And the mechanism involves kind of a two-step addition of hydrogen atoms, one to the carbon and one to the oxygen of the carbonyl. So the first addition is going to involve the resonance structure that we had talked about earlier, where we have the charge separation. The oxygen picks up a negative charge, the carbon picks up a positive charge. So when we do this charge separation, we can see an opportunity for a hydride to add. Now, what's a hydride? A hydride would be an H minus. Now, as we'll see later in this lecture, it's not just any old H minus, but it's H minus I. IDE is the suffix for something that's negatively charged, like chloride, fluoride, bromide, that sort of thing. So hydride as opposed to hydronium or hydrogen cation. Okay, so it's H minus. Now that's going to add, because opposites attract in electrostatics, that's going to add to the carbonyl carbon, giving us this structure. Now this structure looks like a deprotonated alcohol. That's what it is. That's an alkoxide. Alkoxides are strongly basic, and so they will add to mild acids, mild Bronsted acids. So we could take that alkoxide intermediate, draw it down here with its negative charge, and then just add H plus. And this will occur during the reaction workup. That is when you're cleaning up the reaction, removing salts and neutralizing charges, you may add a little bit of dilute HCl to the reaction to encourage some sort of protonation event where the negative charge grabs the H plus from some dilute HCl or something. But this happens at the end of the reaction. And that gives us a product where we've now added two hydrogen atoms to the carbonyl, one of which was the H minus. That's the one that did all the heavy lifting. The other one was just an acidic hydrogen, not as big a deal. Okay, so that's the general mechanism. Now let's think about some sources of hydride. Okay, so the sources of hydride would be well, we could start with the ones that we know, which is NaH, or sodium hydride. It turns out, just when we go into the lab, we try this reaction, it doesn't work. NaH is a base, not a nucleophile. Okay, so even though we could cross out the Na and write a negative charge, as I encouraged earlier on in the semester, it just doesn't work here. We're not going to see the H minus add to the carbonyl. So we have to use different types of reagents. So sodium hydride does not work. Okay, we're not going to use sodium hydride. Instead, we're going to use two other reagents that serve as sources of nucleophilic hydride. And they are NaBH4 and LiAlH4. So this first one is called sodium borohydride. And the second one is lithium aluminum hydride. Lithium aluminum hydride. And there are variants of these. Sometimes you see them abbreviated as like LiAH for lithium aluminum hydride, but let's just stick for the with the elemental symbols for now. Okay, so here's the general reaction. We could take a carbonyl and add to it sodium borohydride. And that would give us a product where we've added an H minus now to the carbonyl carbon. And if we follow the reaction up with an H plus workup, which I denote as then H plus, we'll add the H plus to the oxygen atom. Alternatively, we could use lithium aluminum hydride. Now, for now, we're going to assume that these two are identical reagents, but we'll see that the lithium aluminum hydride is a more potent reducing agent. Even though it gets the same outcome for acetone, it's a more potent reducing agent. We'll actually see it do some advanced reactions that sodium borohydride cannot do. Okay, so those are the general reactions. So if you predicted products, you would just show products where you erase the double bond on a carbonyl and replace it with a hydrogen on the oxygen. The other hydrogen is just an implicit hydrogen that you don't have to draw. Okay, so if you predict the products, let's do something more complicated. I guess we could even, let's just stick with one. Okay, so if you saw this and you said NaBH4 followed by then H plus, and I try to always write then H plus, you wouldn't really ever, at least for this class, want to stop this. Okay, I just about gave away the answer. I'm saying here's the situation. We have a question mark here. Okay, the answer would be this structure down here. You're doing the opposite of the carbonyl oxidation that we, or the alcohol oxidation. This is the opposite process. We can go from the alcohol to the carbonyl using an oxidation process with something like the Sworn oxidation. We can go from the carbonyl back to the alcohol with this reduction process. Okay, so I've introduced two new reagents. Let's ask the question, sort of how does this work? Oh, sorry, I didn't mean to jump so far ahead there. Okay, so the way these things sort of work is we first have to consider that we have counterions attached to these. So let's cross out the Na and the Li. They are just counterions. Okay, so if we do that, we get to a structure that's AlH4 negative on the aluminum and BH4 negative on the boron. So both of these, aluminum and boron, are group 3 elements. These are very awkward elements because when they have an octet, they're negatively charged. So they have a difficult choice. Do they want to render themselves always charged, or do they want to get an octet? It's a difficult choice. They're in an awkward part of the periodic table. They wish they were group 4, with carbon and that sort of thing, but they're not. We got to deal with it. Okay, so this is how this works. What we have is we've got aluminum surrounded by hydrogen atoms. Aluminum being a group 3 element, 3 minus 4 bonds minus 0 lone pairs of electrons is a -1 charge on the aluminum. Same thing goes for boron, negative charge. Okay, and they can be countered by lithium, which we cross out, or sodium. And the reason for these particular counterions is just ease of access, ease of preparation. So again, we won't worry too much about these. Now, it turns out that the negative charge in the group 3 element is going to render the hydrogen atoms nucleophilic. Makes the H minus nucleophilic. Now, additionally, the group 3 elements serve as a Lewis acid. Serve as a Lewis acid. And so they will adduct to the carbonyl oxygen. Okay, so here's how we want to think about this oxygenation I about wrote. Sorry about that. Here's how we want to think about this reaction. If we take a carbonyl and we add to it BH4, which I'm going to now draw as a Lewis structure, what's going to happen is we're going to obtain a product where the oxygen has accepted the boron. It's not floating around. It's not necessarily countered by the lithium and the sodium in a super convenient fashion. Rather, the boron is adducting to the oxygen after it has added a hydrogen. So if you look at this, if you want to follow along here, we've got this hydrogen on the boron, for example, that now ends up as this hydrogen in the product. Now, what I've left out of both of these structures is there's a negative charge on boron. So the same thing could happen just having aluminum here if we were using lithium aluminum hydride. Now, it's important to note that this boron with a negative charge can actually still react to reduce other carbonyls. Can still react to reduce other carbonyls. So what I'm saying is that in theory, if you take this molecule, which I had just drawn, and you add it to another molecule of acetone, what you'll get is an outcome where now the boron is bonded to two oxygens and both of the carbonyls have been reduced. That is to say that lithium aluminum hydride and sodium borohydride can each provide 4 equivalents of nucleophilic hydride. Okay, that's pretty interesting. So that's a good use of that word for equivalence. Now, it turns out nobody really does this. We usually just add a molar equivalent and we just kind of add way too many H minuses and then deal with it at the end of the reaction during the workup. Nobody accounts for this. Well, I'm not going to write that. That's not true. People do. It's just common, really. You could say, well, that means that I could add 0.25 equivalents or 0.25 moles of sodium borohydride for every mole of carbonyl that I want to reduce, right? Because if each one does 4, then I need 1/4 of the sodium borohydrides to accomplish the full reaction. Now, typically people just add a 1-to-1 molar ratio and just deal with the excess H minus at the end of the reaction. Okay, these serve as two really fundamental reactions for us, the reduction of a carbonyl, and we're going to use those going forward to reduce other carbonyl-like systems to make some pretty interesting molecules. So be sure to keep them in mind, and if you don't, I'll make you because I'm going to keep talking about them. Okay, all right, have a good one, everybody. That'll do it for this lecture.